For over a century, two theories have shaped our understanding of the universe, one for the cosmic scale, one for the subatomic. General relativity describes the grand dance of planets and galaxies, while quantum mechanics governs the strange world of particles. These theories are the foundation of modern physics, yet they remain fundamentally separate. Their mathematical languages and rules clash, leaving us with a profound puzzle. How can both be true in the same universe? The quest to unite them, a theory of everything, is the ultimate challenge in physics. It's not just about equations, it's about answering the deepest questions. What happened at the universe's birth? What's inside a black hole? Is space-time fundamental? Our current theories break down in extreme environments where both gravity and quantum effects matter, producing nonsensical infinities. Nature doesn't divide itself. The split is in our understanding. We stand at a crossroads, facing the chasm between our two greatest scientific achievements. The journey to bridge this gap has inspired some of the most mind-bending ideas in science. This is the story of that journey, the conflict, the search, and the hope for a unified truth. To grasp the problem, we must first understand the two theories at its core. General relativity, Einstein's creation, explains how mass and energy curve space-time, shaping the cosmos. Picture a heavy ball on a rubber sheet. This is how gravity bends the universe. Quantum mechanics, meanwhile, rules the atomic and subatomic world, where particles exist in clouds of probability and energy comes in discrete quanta. Both theories have passed every experimental test in their domains. General relativity is our guide to the very big planets, stars, galaxies. Quantum mechanics is our guide to the very small atoms, electrons, photons. Their rules are radically different. One is smooth and deterministic, the other jittery and probabilistic. For most situations, this separation works. You don't need quantum mechanics to calculate Mars's orbit, nor gravity to design a microchip. The trouble starts when both realms overlap. When the very big meets the very small, our maps of reality no longer align. That's where the real mystery begins. The need for a unified theory becomes unavoidable. Let's zoom in on general relativity, Einstein's revolutionary theory of gravity. Before Einstein, Newton's gravity worked for most things, but couldn't explain anomalies like Mercury's orbit. Einstein's insight, gravity and acceleration are indistinguishable. The principle of equivalence. Imagine being in a windowless elevator. You can't tell if you're feeling gravity or acceleration. This led to the idea that gravity isn't a force, but the warping of space-time by mass and energy. Massive objects curve space-time, and this curvature guides the motion of everything else. Time itself is affected by gravity. Clocks tick slower in stronger gravitational fields, a fact essential for GPS accuracy. General relativity predicted gravitational waves, ripples in space-time, confirmed a century later by LIGO's detection of black hole mergers. The theory describes a smooth, continuous geometric universe, a grand cosmic stage. Its predictions have been stunningly confirmed, but only on the largest scales. Yet, it cannot explain the quantum world. Now, let's dive into quantum mechanics, the theory of the very small. Here, certainty vanishes, particles exist in clouds of probability, and energy comes in indivisible quanta. Wave-particle duality means electrons and photons behave as both waves and particles, depending on how we observe them. Measurement itself changes reality, collapsing possibilities into a single outcome. The Heisenberg uncertainty principle sets a fundamental limit. The more precisely you know a particle's position, the less you know its momentum. Nature is inherently fuzzy at its core. Quantum mechanics isn't just weird, it's incredibly successful, underpinning all modern technology from computers to lasers. It explains the forces binding atoms and powering the sun. Despite its strangeness, it's the most precise theory we have for the microscopic world, but it cannot describe gravity. For most purposes, physicists use general relativity and quantum mechanics separately. Relativity handles the smooth curves of spacetime, quantum mechanics, the jittery world of particles. The problem arises in extreme situations, where things are both massive and tiny. Here, the two theories collide, and their mathematics falls apart. Relativity sees spacetime as smooth and continuous, like a rubber sheet with no smallest unit. Quantum mechanics suggests the universe is a turbulent sea at the smallest scales, a quantum foam. When you try to combine them, the equations explode with infinities. It's like mixing two incompatible maps with no conversion. Relativity can't handle quantum chaos. Quantum mechanics can't operate on relativity's smooth stage. Both are brilliant, but fundamentally at odds. The universe demands a single rulebook. We just haven't found it yet. The clash of theories becomes unavoidable at black holes' centers and the universe's birth. General relativity predicts singularities, points of infinite density where its laws break down. Quantum mechanics forbids such infinities, suggesting something else must happen at these extremes. To understand black holes' cores or the first instant of the Big Bang, we need a theory that unites gravity and quantum physics. Without it, the universe's most profound mysteries remain unsolved. Physicists have proposed bold ideas to bridge the gap, most notably string theory and loop quantum gravity. String theory imagines the universe's building blocks as tiny vibrating strings, each vibration creating a different particle. Gravity emerges naturally as one mode of vibration, the graviton. But string theory requires extra hidden dimensions and remains mathematically complex and untested. Loop quantum gravity takes a different route, applying quantum rules directly to space-time. It suggests space is woven from tiny, discrete loops, atoms of space itself. This granular structure avoids the infinities that plague other theories. Both approaches are elegant, but neither is complete or proven. They offer radically different visions of reality. The search for a testable, unified theory continues. For a theory to be scientific, it must be testable, but quantum gravity operates at the Planck scale, far beyond our reach. The energies needed to probe these scales are unimaginably high, impossible with current technology. Our best particle accelerators are nowhere near powerful enough. So, physicists hunt for indirect clues, tiny effects in cosmic rays, or subtle imprints in the cosmic microwave background. Some theories predict that spacetime's granularity could affect the speed of high-energy photons from distant explosions. So far, no such effects have been found, but the search continues. Scientists also scan the afterglow of the Big Bang for quantum gravity's fingerprints. The evidence is elusive, but each new observation narrows the possibilities. The challenge is immense, but not insurmountable. Despite the difficulty, new tools are emerging. Artificial intelligence is helping physicists sift through vast data, spotting patterns humans might miss. AI is also exploring the complex mathematics of theories like string theory, searching for new connections. Quantum computers, still in their infancy, could one day simulate quantum gravity, letting us test ideas virtually. These technologies may open doors to discoveries we can't yet imagine. The quest for a unified theory is about more than equations. It's about curiosity and the drive to understand our place in the cosmos. Even if the answer remains out of reach, the journey itself pushes science forward. The search for